Right, I hope everyone's doing fine. For this discussion, we will be talking about Darcy's Law, which describes how groundwater moves in the subsurface. Right, Darcy's Law is about the quantities that govern the flow of groundwater, and Darcy's Law takes the following inputs. First is the hydraulic gradient, and then hydraulic conductivity, and then the cross-sectional area of the subsurface flow, right? Now, hydraulic gradient is all about the driving force, all right? We're talking here about the change in potential energy of the flow, and the bigger the change in potential energy, the more driving force you have. And then the next is hydraulic conductivity, which is all about the capacity of your aquifer, which could be soil or fractured rock. It's about how it's about their ability rather to transmit water. Okay? And then last is the cross-sectional area of the flow, which will definitely depend on the thickness of the aquifer, particularly how thick the thickness that is saturated or the thickness of the aquifer that actually has water. All right. Now let's see the Darcy's law equation. It is defined as Q or the discharge or the uh, volume per unit of time. All right, Q is equal to K or the hydraulic conductivity multiplied by A or area, and then multiplied by the quantity of delta H or the change in hydraulic head divided by the length of the flow. Right? So delta H over L is your hydraulic gradient. And for the purposes of most groundwater calculations, it is really difficult to represent the flow as a 3D flow. And for most calculations, the L or the length of flow is typically simplified as a one-dimensional quantity. Okay, so meaning it's L is about point going from point A to point B, right? Okay, so most problems in groundwater flow is simplified into 1D problems. Right, so this quantity, this equation will give you a discharge or groundwater flow in units of cubic meters per second. And you can also actually get the velocity of groundwater flow by dividing this quantity by area A. Right, so you can just take hydraulic conductivity K multiplied by the hydraulic gradient, and you will get the groundwater velocity, right? Now, this is what I was talking about. These are the other forms of the Darcy's law or Darcy's equation. You have V or Darcy velocity is equal to basically hydraulic conductivity K multiplied by hydraulic gradient I. All right, this is a schematic showing the elements involved in the Darcy's equation. And as I have discussed earlier, In hydrogeology, most of the time we just simplify the problem into a one-dimensional problem. So for here, for example, most of the time when we are talking about flow of groundwater, the default point of recording here is the top of the water table. So let's say we're talking about groundwater flow from point A to point B. All right. So what are the inputs that we need for this problem? First, of course, is K, or the hydraulic conductivity, which is all about the hydraulic conductivity of this aquifer, right? And we can get that number from a variety of tests, including well tests, or the in situ or the field testing of the aquifer, which we will be discussing later, and also the laboratory testing, which involves testing samples of your aquifer outside the field, right? So now we have K. Another important parameter, of course, is your I, or your hydraulic conductivity, which is all about the delta H, or your hydraulic head loss, divided by the length of the flow. As you will see here, point A going to point B, you have a change in the elevation of your water table. And for this scenario, all right, for this scenario, this is just an ideal example. All we need to know is to determine the hydraulic head loss, which can be approximated by getting the difference in the elevation. All right. So that is your delta H. So the difference in elevation is your delta H. Although this is not always the case, and we will be discussing that limitation later. Okay. So this is just valid for unconfined aquifers, and we will be discussing other variations later on. But for now, let's just accept that the hydraulic head loss is just, or can be approximated by the difference in elevation of their water tables. So you now have delta H, and then finally your length of flow is your L, or your distance. Now, strictly speaking, the distance from point A to point B is an inclined path. All right, so this is slightly inclined. All right, but for simplification purposes, we just take distance L as the plan view distance. Right? So we just take distance L as a plan view distance for simplification purposes. Right? Now that gives us I. So we now have I. And then finally we just need the cross-sectional area A, which will depend on the extents of your aquifer. Right? So that's how Darcy's law works. All right. This is just an example for an unconfined aquifer. All right. Now let's talk about the inputs individually. All right. Now let's talk about hydraulic head, or the piezometric level. Right now, note that hydraulic head is expressed in units of length. right? Typically in units of meters or feet. And strictly speaking, hydraulic head represents the mechanical energy per unit weight of the fluid. So basically, hydraulic head is a measure of how much water, how much equivalent height of water column is overlying a certain point. Okay, so instead of expressing the pressure in units of kilopascals or pascals or psi, we just remove the unit weight of the fluid, since water is typically, or water has a constant unit weight, or more or less has a constant unit weight. We can just divide the pressure by the unit weight of water, and you will get uh, a number that is expressed in units of length. All right. Okay, so hydraulic head is sort of a number that represents the pressure that is being exerted at a point, but you basically take away the unit weight of water, and we are left with a number that is expressed in units of meters. Now, total hydraulic head at any given point is is a summation of hydraulic head due to the pore fluid pressure, which is typically due to the due to confinement, right? In the case of confined aquifer, and also due to the weight of the overlying water column. Okay, so for this illustration, okay, this is an unconfined aquifer, so we don't have confinement in this point, but we do have an overlying water column, which is this column. So this column of water is exerting pressure at the bottom in this point. Okay, so that is H sub B. We also have H sub Z, which is the elevation head due to gravitational energy. And this number is only important when you are talking about, or when you are comparing two points with different elevations. Okay, so let's talk about that later, or I'll be more detailed with examples, right? Now, in practice, hydraulic head is typically measured or determined from the rise in water levels using wells or piezometers. So note that when you are trying to measure the hydraulic head or the piezometric level of a of a of an unconfined aquifer, the piezometric level is just equal to your groundwater table or groundwater level. So they are the same. Now, this one changes when you are dealing with a confined aquifer. So you have confinement, or basically your aquifer is being held down or being pressed down by your overburden. Okay? So in this case, once you insert a piezometer or a well, the water will surge out of your well, and it will be definitely greater than, so your piezometric level is definitely greater than your groundwater table for confined aquifers. Okay? All right. All right. Just to give you a recap, the pressure head component for aquifers. All right. So pressure head is just a component of your hydraulic head. For unconfined aquifer conditions, the pressure head is all about the height of the water column that is existing above a certain point. So it depends on your measurement point. If you have a height of water column existing above that measurement point, then you have uh, a pressure head. Now, for confined aquifer conditions or aquifers that are being pressed down by a confining layer, your pressure head is a combination of pressure due to your height of an overlying water column, if there is a water column above that measurement point, and you also have pressure due to confinement. Now we can calculate pressure head, all right, or based on how much pressure your fluid is exerting on a certain point. So given a fluid pressure, you can convert that into pressure head, which is expressed in meters. So H sub P, or pressure head, is equal to pressure of your pore fluid raw, or P, sorry, divided by raw, or the unit or the density of the fluid, times G, or the acceleration due to gravity. So note this quantity is just the your gamma, or the unit weight of water. Right? Okay, so yeah, it's quite simple. You just take pressure and then divide it by the unit weight of water, and you will be getting the pressure head, which is expressed in meters. Okay, so that just shows how or why we express hydraulic head in units of meters, because we can always easily convert it by multiplying or dividing it by the quantity of the unit weight of water. Now let's have an example. Alright, for this example, we have a confined aquifer. So this is a confined aquifer because you have confinement due to an overlying clay layer. Okay, so this is your confining layer, your clay. That's your confining layer. And then below your confining layer is your aquifer, which is consisting of sand. Now, what happened here is we inserted a well, or a piezometric or a piezometer, okay? And then, so this is nominally the groundwater level in here, okay? Nominally, this was the groundwater level, but upon inserting a piezometer or a well, the the water shot up, or it went up due to pressure, due to confinement. Okay, so the water rose in the piezometer, and we registered a piezo level rise of 10 meters. Okay, all right, all right. So what is the or how much from this given, how much pressure or pore pressure is acting on this top of the aquifer, or rather at this point. All right. So yeah, what is the total pressure acting on this point at the top of the aquifer given this piezo level rise of 10 meters? What we do here is we go back to the equation. H sub P is equal to pressure divided by your rho, or your density of water, times your gravitational acceleration. So pore pressure head is equal to 10 meters. All right. And then we don't know the pressure, so we leave it as P. And then the density of water is 1 ton per cubic meter. And then the acceleration due to gravity is 9.81 meters per second squared. All right. Now we just rearrange the equation such that the total pore pressure reacting at this point is just 10 times 1 times 9.81, and we get a value of 98.1 kilopascals. All right. So that is all about confinement. All right. The 98.1 kilopascals is all about confinement that is acting at this point. Now, we have no other sources of pressure acting at this point, all right? Because there is no overlying uh, body of or column of water on top of this point. So this surge in water table is all about due to confinement or pore pressure. Okay, so we don't have any water column acting at this point. So pore pressure is purely due to confinement. Now, if we are talking about this point at this bottom of the aquifer, all right. Now, if you're talking about the bottom of the aquifer, or if you're at this point, the pressure would be equal to your HP would be would come from two sources. First is the water column acting above this point. Okay, so you have a water column above acting above this point, and you also have pressure due to confinement, which is measured by the piezo level as 10 meters. All right, so the pore pressure acting at a given point will depend on where the point is situated. All right. So for this question, is the amount of pore pressure acting at the bottom of the sand aquifer the same? So it's a big no, because at this point you have additional pressure acting due to the column of water of overlying column of water. Okay, aside from the uh, pressure due to confinement. Now the second example, for this second example, we're given an unconfined aquifer. All right. So this water table, so your groundwater table level is equal to your piezometric level for an unconfined aquifer. So we don't have to worry about confining pressures in this at this point. Our only concern for unconfined aquifers is the height of water column acting at a particular point. All right, going back to the example, we are given a slope failure surface with a perched aquifer and there's an overlying water column of 20 meters. Assuming the aquifer and the slope is unconfined, how much pore pressure is acting on the indicated point of failure surface? All right, so now note this example is a geotechnical example. All right, although this course is supposedly more focused on the water resources component, I decided to just insert this example for full appreciation of the power of hydrogeology, even in other applications. So this is a profile view of a slope. All right, so that is your slope. This is your slope profile. So it's quite steep in this part. So that is your profile. And you have a potential failure surface defined by this line. Okay, so the slope can fail and can move this way. All right, and one of the forces that are acting on your failure surface is your water table. Okay, pore pressure can PP or pore pressure can decrease your effective stress. Okay, so sigma. Okay, so effective stress or sigma can be decreased by pore pressure. Okay, so the less effective stress you have, the less you also get decrease in your shear strength. Or to just dump it down, the more pore pressure you have acting on your failure surface, the less strength it will have, the less effective strength it will have. All right, so we gotta know how much pore pressure or how much total pore pressure is acting at this point. So we have this height of water table, which is 20 meters. All right, and all we have to do is go back to the equation. So uh, pressure head is equal to density of water, or rather, hydraulic head is equal to pore pressure divided by density of water time por- pressure divided by the quantity of density times gravity. Okay, so P divided by gamma, or P divided by unit weight. And what we get is pore pressure is equal to 20 meters of water of your water column times 1 ton per 1 ton per cubic meter times 9.81, and we get a total pore pressure of 196.4 kilopascals. All right, so that's the amount of pore pressure acting at this point. Okay, okay, so reminder, this is an unconfined aquifer, and the only pressure acting at this point is just the water column. Okay, so we don't have to worry about pressure due to confinement. All right. So let's say, let's go to this question. If the perched aquifer is bounded by a confining layer at the top, will the pore pressure acting on the failure surface stay the same? So if this layer is a confining layer, all right. So confining layers are basically pressing down your aquifer, all right. So you can imagine a balloon being pressed down, or a Tetra Pak. So to see your favorite juice, or your your Tetra Pak is being pressed down. Of course, there will be an increase in pressure of the in the fluids inside, and you will be getting additional pressure due to confinement. All right, so the pore pressure will definitely change. It will increase, so no. All right. So if this is a confined this is actually a confined aquifer, you should expect a much bigger pressure acting at this point. All right. So yeah, the type of aquifer matters, or the aquifer conditions matter. Okay. They definitely exert an influence on the pore pressures. Okay, being exerted at a certain point. All right. So in the previous two examples, we were just talking about a single point, and we were concerned with the pore pressure. Okay. For this example, we will be talking about hydraulic head difference, or delta H. And we will be also talking about two stations. All right. So we will be talking about two measurement points, or two stations. And again, our example here is an unconfined aquifer with two stations, station 1 and station 2. All right. And in station 1, the groundwater table elevation is 230 meters above sea level, or MASL. So MASL means meters above sea level. Please be familiar with these terms. Right? You will be encountering them a lot once you start working in the geotechnical and in the hydrogeological field. Anyway, going back, station 2 has a groundwater table level of 250 meters above sea level. So station 1, 230, station 2, 250. All right. Now, our problem is, what is the hydraulic head difference between the two groundwater table levels in the two stations? Now, this is quite simple, particularly because our points of reckoning are located at the top of their respective groundwater tables. So there is no water column acting at these points. Okay, so we are at the top of the groundwater table, so there is no water column acting at these points. Okay, all right. So going back, hydraulic head difference is just equal to H2 minus H1. So all right. So hydraulic head in station 2 minus hydraulic head in station 1. And this is just equal to uh so your hydraulic head in station 2 is just equal to hydraulic head due to elevation plus hydraulic head due to pressure. Okay? And the same is, you just have the same case in station 1. So the hydraulic head in station 1 is just the summation of hydraulic head due to elevation and hydraulic head due to pressure. All right. Now, looking back, we have we don't have any source of hydraulic head pressure at these points, because first, it is an unconfined aquifer, so we don't have pressure due to confinement. And second, we don't have an overlying water column at these points. Okay, So you don't have water columns overlying at these points. So you don't have pressure due to uh, an overlying column of water. So I hope that sounds clear. Hence, pore pressure head is 0. All right. You don't care about pore pressure head at this point. They are not. They're not present at these 2 points. So we are only concerned about the hydraulic head due to elevation, and that is basically, and that bring us to a hydraulic head difference being equal to 215 minus 230, and we get a hydraulic head difference of 20 meters. All right. So note that the value is positive, so that's positive 20 meters, which means that the flow will be going towards the second term in this point. So the subtractor, I hope I'm using the correct word. So the subtractor is the second term here, which is H1. Okay. So you have a positive value. It means that the direction of the flow will be going towards H1 or the subtractor. All right. Right. So always remember that changing the measurement points and changing the aquifer conditions will always affect the hydraulic head difference. Now let's talk about hydraulic gradient I. This number basically represents the rate of change in hydraulic head per distance. Okay, so it is basically delta H divided by the length of the flow, or change in hydraulic head divided by the length of the flow. And note that groundwater flow will always move from a higher hydraulic head to a lower hydraulic head, like in physics, all right? Objects always move from an a position of higher potential energy to a position of lower potential energy. And the same just applies to groundwater flow. Always goes from higher to lower hydraulic head. And there's also no such thing as strictly horizontal groundwater flow except for a few limited cases. Although for most problems, since we are talking about one-dimensional problems, most of the time we just assume a purely horizontal groundwater flow because we are trying to simplify the problem as a one-dimensional problem. Okay. All right, where aquifer recharge is dominant, the flow is vertically downward. So basically, when you are talking about recharge areas in a watershed, most of the groundwater flow is just going vertically. All right. So yeah, mainly because your water table is really deep. It's really going very deep, and the only direction for your water to go is just to go downward. In a discharge area, such as a surface stream, the flow has an upward component. Okay, so take note of this statement. All right. Groundwater flow is always dictated by the change in hydraulic head. There are cases where your groundwater can actually move upward in terms of elevation. Okay, so as long as the hydraulic head allows your groundwater to move upward, it can move upward. Okay, right. So that's just the same statement here. Groundwater flow can flow upward when the direction of as long as the direction involves a downward hydraulic gradient. So that's quite confusing, but you can just look at this point. Okay, so you have here a uh, hydraulic head of 30 meters. All right, and then at this part you have hydraulic heads of 10 and 20. Okay, so at this point the hydraulic head is actually decreasing as you go upward. So that will allow your groundwater flow to move upward or uphill or yeah, upward. Okay? What can be causing that? So the typical case here is you might be having a confined aquifer. So this might be a confining layer. So your water is basically moving downward in here. All right? Moving downward. It cannot go past this confining layer. All right? So it just continues downward. All right? It continues down the lower elevations and lower hydraulic heads until it accumulates a lot of pressure. Now, at this point, it has accumulated a lot of pressure, and at this point, there might be an opening like a stream. So, at this point, you have a lot enough pressure to actually break out and move upward. All right. So, at this point, it has enough pressure to move upward, right, and exit either as a spring or as a water that is contributing to stream flow. All right. So yeah, definitely groundwater can always flow upward as long as the hydraulic gradient allows it. And this can occur in confine when you have confining conditions. All right. So as you have seen here, the confining conditions basically restricted the movement of groundwater and allowed the groundwater to accumulate its pressure. Okay, until a point where it can actually exit by moving or by flowing upward. Now, our next topic is hydraulic conductivity. All right, so let's differentiate hydraulic conductivity from permeability. All right, first, permeability is an intrinsic property of your porous medium only. So permeability is just all about your aquifer or your soil or your rock. And this is, of course, this is also about its ability to transmit fluids. And this is expressed in either centimeter squared or meter squared or in units of Darcy. You can imagine permeability as a number that is sort of related to the surface area of your porous medium. Okay? So the bigger the the surface area of the grains in your porous medium, okay, the bigger the sorry, permeability is like a number that represents the interconnected surface areas within the grains of your soil or rock. Okay, so the more surface area that is interconnected, the more you have pathways for flow you have. And then hydraulic conductivity, on the other hand, depends. on both properties of your medium and your fluid. All right, so we have hydraulic conductivities for water, for air, for oil, for salt water, and so on. But for hydrogeology, we are mostly concerned with just the hydraulic conductivity of water. And hydraulic conductivity is expressed in centimeters per second and in meters per day and so on. And more importantly, for most for most discussions, all right, our focus is mostly on hydraulic conductivity. And you might be confused in some books or in some textbooks. They interchangeably use permeability and hydraulic conductivity. All right, so in that case, you just have to look at the units being used. All right, if they are using units of centimeters per day, meters per day, feet per second, and so on, they are probably talking about hydraulic conductivity. All right, and then you also have here the relationship between permeability and hydraulic conductivity. So permeability, or Ki, is just equal to hydraulic conductivity multiplied by the kinematic viscosity of the fluid and the acceleration due to gravity. All right. Other notes note that hydraulic conductivity can vary within a space, or it can be heterogeneous. This is especially applicable for aquifers like interbedded sandstone, siltstone. So you might have silt or mudstone, and then you have sand, and then siltstone, and then sand. So in this point, your you will have small hydraulic conductivities in your sand in your siltstone, and then you'll be having big hydraulic conductivities in your sand. All right. So that is heterogeneous. What is an anisotropic? Anisotropic um, um, means you have different hydraulic conductivities depending on the direction of the flow. All right, so you might have a bigger hydraulic conductivity in the horizontal direction compared to the vertical direction. But it depends, all right? It always depends on the aquifer conditions, right? So these uncertainties should always be expressed or accounted for in your models or in your calculations, all right? Another fact, and hydraulic conductivity is also related to your effective porosity, or how much pore spaces in your rock or soil are actually interconnected. Okay, so for example, you have a vesiculated basalt which is intact, meaning it's not fractured. All right, so you have a fresh vesiculated basalt, and it will have a lot of vesicles, so it has a high porosity or a lot of air spaces, but these may not be interconnected, so they will have a low effective porosity. All right. Now, note in rocks can have secondary porosity, which is due to faults, fractures, or joints, which can enhance your effective porosity. And As a consequence, they can increase your permeability or hydraulic conductivity. All right. And another note for hydraulic conductivity is that hydraulic conductivity increases exponentially with grain size. Right? So there is an exponential increase with the change in grain size. So in hydrogeology, identification of the soil is very sensitive or very important. All right, because soil types, right, can drastically change your estimate in your hydraulic conductivity. Okay, so you can see here from fine sand to clean sand, you can get a jump of around 1 to 100 meters per day. So that's 100 times change within basically the same grain size family. All right. So, or if you jump from sand to gravel or purely gravel, you get a jump of 10,000. All right, and that is a very big number. All right. So, what's the takeaway here? Soil types can give you very unreliable estimates for hydraulic conductivity. Okay. So most of the time, laboratory testing in hydrogeology is just a supporting data. It's mostly just a auxiliary data. We always rely on in situ testing. All right, in situ testing like well tests, slug tests, and other field testing is very important in hydrogeology. Okay, because they more or less account for the variabilities in your aquifer conditions, unlike laboratory testing or using correlation tables. All right, these correlation tables and lab testing can easily mislead you in terms of numbers. Now let's discuss the second part, which is all about the types and calculations of groundwater flow. All right, so there are these are the factors which can help us determine the type of groundwater flow, and as a consequence can help us select the relevant equations or relevant governing equations that we should be using. All right, so we should be wary of the hydraulic conditions in the aquifer. All right, does it vary a lot per location and time? Does it, does it, or does it not change a lot? You also have your cross-sectional area in the flow. So for example, when you have a confined aquifer, okay, so you have confinement, which basically fixes your cross-sectional area. Okay, so in a confined aquifer, more or less your cross-sectional area is constant. While for an unconfined aquifer, all right, the water table can freely go down, can go up and down. So your cross-sectional area can vary through time. Okay, and of course time for, yeah, as shown above, time is important. Okay. All right, so let's talk about the different conditions like steady state conditions. In steady state conditions, your hydraulic head and your hydraulic gradient are constant. Okay? So meaning your water table is more or less not moving. So your water table is not moving. It is fixed. Okay? And then your water table on the other end is also fixed. Okay? So when you have water tables or hydraulic heads at two different points that are fixed, you end up with a constant. You also end up with a constant hydraulic gradient. Okay, and this can occur in both confined and unconfined conditions, right? Although note that steady state conditions in the real world are rarely satisfied. I mean, theoretically, you have a few applications for steady state conditions. So you have to have, for example, an aquifer that is large enough to be negligibly affected by water withdrawals or water pumping to have a steady state condition. Meaning, if you pump out water from this aquifer, the water table will not change a lot. All right. Although there are other applications for steady state conditions, which I'll be talking about later. Okay, so one important application of steady state conditions is the quasi steady state. This is all about uh we we are trying to approximate, all right, a condition that is not really steady state, but we can approximate a particular part as a steady state. So to be more precise, I'm talking about the apparent stabilization of hydraulic head after withdrawing water from a well. Okay, so when you're pumping out water from a well, okay, so you're pumping out some water. Right, so the response of the water table is to lower down, all right, initially. It will go down initially, but after some period of time, so you're just constantly pumping out water. After a certain period of time, your water table will eventually stabilize. All right, it will eventually stabilize for a short period of for a certain period of time. All right, so it can stabilize briefly to a certain level, and we can approximate that state as a quasi steady state. All right, so what are the factors that affect the stabilization of water level? So it could be due to inflow of water into the systems, such as a nearby surface stream, or due to the increasing influence of your pumping. Okay. Okay. So quasi steady state is all about a temporary stabilization of water levels. By temporary, I mean if you start you s- if you once you stop your pumping of water, this whole thing can change again. Or probably after a long period of time, the water table can slightly go back to its normal levels, right? And so on. So quasi steady state is all about a particular period of time, right? And the quasi steady state approximation is, of course, it's very useful for certain calculations. Okay, because it simplifies all your calculations. And the cases where you cannot apply quasi-steady state approximation is when you are withdrawing too much water. Okay? When you are withdrawing a lot of water, such that the recharge from nearby areas cannot cope up with your withdrawal. Okay, so for example, if you are pumping out water from an aquifer, okay, so you're pumping out water and you are getting some inflow or recharge from nearby areas. Okay, so the nearby areas are trying to stabilize or hold this water table level. But in the case of you withdrawing a lot of water, okay, the recharge from nearby areas might not be enough to actually stabilize or cope with this withdrawal. So you will end up with a water table that is just that is decreasing and decreasing over time. Okay, so at that point, for this case, this is not a quasi steady state anymore. So this is a unsteady state, right? Because your because your water table or your hydraulic head is changing over time because the recharge from nearby areas cannot cope up with your groundwater withdrawal. Now we have transient or unsteady state. So this basically involves a hydraulic head and a hydraulic gradient that is changing through time. So if your hydraulic head is lowering or going up or down through time, that means your hydraulic gradient is also changing. So it's not a steady. It's an unsteady state. All right. And unsteady state equations is are what you need to fully describe a or typically this is what you need to fully describe groundwater flow in a system. For example, resource or aquifer management and so on. And one of the good indicators that show that you're dealing with unsteady state conditions is when you have storage parameters, you have storage coefficients, you have other transient states. Okay. Although for most of hydrogeologic calculations, particularly for well testing, you will be mostly dealing with unsteady state conditions. Okay. For well testing. Okay. So you might be using unsteady state and some quasi steady state conditions. All right, so let's talk about other descriptors or parameters of aquifers. So let's talk about transmissivity of porous aquifers. So transmissivity is this is basically just the product of aquifer thickness B times the hydraulic conductivity K. And the significance of transmissivity is that you can use transmissivity to calculate well yield or how much water can the well produce. All right. So you just multiply the area of well influence times geometric factors and you will get well yield. All right. So transmissivity times the area of well influence times geometric factors, you can get well yield of an aquifer. Other notes, transmissivity increases with increasing hydraulic conductivity, which is quite obvious as you can see here. increase in hydraulic conductivity will increase your transmissivity. Also, can increase, thicker aquifers have higher transmissivity. And also note that, as discussed earlier, hydrogeologic parameters like hydraulic conductivity and transmissivity are best determined from long-term field pumping tests. All right. This is important. You have, as much as possible, you want to have uh, long-term pumping where you are more or less having a good approximation of your quasi steady state. Okay. So you want a long-term pumping test to get a good quasi steady state conditions. Okay. The longer your pumping test is, the more reliable your data is. Although this can be very expensive to do. Although note that in well development projects, water wells are long lifespan projects. They can go from 20 to 50 years to 100 years. So as much as possible, you want to have a very reliable number because it's a long-term project. Now let's talk about the equations that are used to determine the well or aquifer parameters. Okay, so these are the equations that we use to analyze well testing or well pumping data. First is the theme equation. Theme equation is to make things simple. This is what we use when you have multiple well data. All right. So what happens here is we can use the theme equation when you have a more or less quasi steady state radial flow towards a well. And these are satisfied by the following conditions. So you have a fully penetrating pumping well. So meaning if this is your aquifer, it means that your well is fully penetrating the whole thickness of your aquifer. So this is a fully penetrating well, and this is a partially penetrating well. Okay, fully penetrating, partially penetrating. Other conditions for a quasi steady state is you have to have a confined aquifer so that your area or thickness or your cross-sectional area is constant. Okay, so as discussed previously, confined aquifers, all right, so you have a confining layer which basically limits the height of your water table, and you have a constant area in a confined aquifer. Okay, because confinement prevents your water table from fluctuating. So confined aquifer is necessary for a quasi-steady state, and you also have to have a impermeable aquifer base level. So this layer beneath the aquifer should also be impermeable, so you don't get water leaking in and out of your bedrock or your base. And you also should not have any vertical recharge from adjacent aquifers or aquitards. So if this is your aquifer, all right, sorry. So if this is your confined aquifer, so you have aquifer 1 And you also have overlying aquifers like Aquifer 2. So if Aquifer 2 cannot recharge Aquifer 1, then you have a non-leaky aquifer. But if Aquifer 2 can actually penetrate through the confining layer and give water to Aquifer 1, then that is called a leakage. Alright, so your aquifer is then leaky. So what does that mean? It means that your aquifer 1 is actually getting water from other areas, and that actually changes the hydraulic head, the effective hydraulic head of your aquifer. Okay, because it has connections to other, it is technically connected to other water table levels. Okay, so that changes everything in your calculations. All right, so the use of the theme equation is that it can be used to estimate aquifer transmissivity and other aquifer parameters. And the main requirement of the theme equation is you have to have at least two monitoring wells and one pumping well. All right, for you to be able to calculate the hydraulic head and other parameters. So minimum you need at least three wells to be able to use the theme equation. Okay, so it's quite limited. So it has a lot of limitations. And this is just the equation, the theme. This is just the form of the theme equation. You have your well pumping rate or your discharge, which is typically expressed in cubic meters per second or per day. And then you have your well radius. All right. All right. So you also have well radius, which is literally the radius of your well. So if this is your well, so let's say this is a close up of your well. So just look at the diameter of your well divided by 2. That is your well radius. Okay, so just look at the this part. Okay, so that tiny radius is the well radius. Okay, so it's so literally the radius of your well or the borehole well diameter. Hydraulic head in the well or H sub W. Alright, so this is the hydraulic head in your well is basically just the difference in head or this is basically the hydraulic head that is existing at the bottom of your well. Okay, so this is the bottom of your well. So you just measure the height of water column that is existing above that bottom, and that is the hydraulic head of your well. Other parameter is the hydraulic head at a distance r. So you just pick an arbitrary distance. All right. Look at the bottom. So reckon from the bottom of the aquifer and just look how much water column is existing above that point. Okay, so that's your hydraulic head. Although you have to factor in, of course, the effects of confinement. Okay, sorry. So these hydraulic heads are equal to hydraulic head due to pressure. So that is Sorry. So these hydraulic heads are due to water column plus pressure due to confinement. Okay. All right. So you also have big H is the initial hydraulic head. So that is the hydraulic head before the pumping started. You also have B, which is the thickness of your aquifer, which is this one. That's your B. You also have the radius of well influence, or big R. Okay, so there are various ways to approximate radius of well influence, but this one mostly depends on the parameters of your well, which will be discussed in the exercise. And then S sub W, which is the drawdown in the well. So drawdown is the drop in water table level due to pumping. So drawdown due to pumping. And finally, you have big K, which is your hydraulic conductivity of your aquifer. All right. So the theme equation, I think, is tackled in the exercises. So I won't be delving on the details of that. Now let's move on to the Thiess equation. Okay, so don't be confused with the theme and the Thiess equation. Thiess equation is a more practical equation because we can use it for a single well data. Okay, so it's this sort of cheaper to implement. And the Thiess equation is still, of course, about transient or time-dependent groundwater flow. And this is useful again for a fully penetrating well in a confined aquifer. And the Thiess equation, the uses of it is that you can get the values of aquifer transmissivity, which can give you the well yield. And you can also get the storage coefficient of an aquifer, which can give you a lot of important parameters, which we will be discussing later in this course, and drawdown. Okay. So, in short, this equation is what you need. You need it when you are developing a water well. Okay, so you can get the values that are necessary to develop a water well. All right. And since the Thiess equation is a transient equation, it allows us to determine aquifer parameters without drawdown stabilization. So this is an important feature of the Thiess equation. You don't need drawdown stabilization. You don't need long-term pumping. Okay, so you don't need long-term pumping to be able to use the Thiess equation. And another feature is that you only need one well to be able to conduct the Thiess equation. So as a result, the Thiess equation is a very popular analysis method used in a lot of pumping tests. And there are actually a lot of variations of the Thiess equation that allows it to be used to confined aquifers, unconfined aquifers, and a lot of other aquifer conditions. All right. Now, this is the basic form of the Thiess equation. As you can see here, You have here S or 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 drawdown. So this is S is drawdown. Q is the pumping rate of your aquifer, which is kept constant during the testing. T is transmissivity, and then WU is the well function. Okay, so the well function is an important feature of the Thiess equation because it allows for a modular application of the equation. So the well function can be modified for different variations of aquifer conditions. Okay, so you have different well functions for different aquifer conditions. And then basically we get the well function WU using the Thiess type curves. All right. And what we do here is we basically print out or we first plot the drawdown time versus time. So what is happening in the aquifer testing is you're basically pumping out water at a constant rate. So you're constantly pumping out water from the well. All right. And what we do is we periodically, or rather, so pumping is taking out water from the well, and that will induce or cause the water table to actually go down. So you're having a drawdown due to pumping. So that drawdown or S is actually being recorded. Okay, so we are recording S through time during a well testing. So you're constantly pumping out water. And what we do here is we are monitoring as well the drawdown through different time intervals in the well. Okay, so once we get S through time, we plot it in a drawdown versus time plot. So we plot this data, and then to to be able to use the Thiess equation, we have to overlay the Thiess curve, which will allow us to get WU and also U. All right, so we get those numbers, and then once we get U, we use it. We use this equation to we plug in U to this equation, and then we start solving for the other well parameters like storage coefficient, transmissivity, and so on. Okay, so it's quite a tricky part, but the Thiess equation is all about getting a drawdown versus time plot, and then using the Thiess curve to visually get U and WU, and then you use this equation to solve for transmissivity and storage coefficient and other well parameters. Now, other notes, the Thiess type curve is a log-log graph of W versus 1 over U and is used to match the data observed in the well test data. Now, let's run through again how the Thiess equation is used. To one part of doing the Thiess equation analysis is doing the Thiess curve matching. So step one is we do a drawdown versus time data. So we plot it in a log-log plot, okay, which is basically typically in meters versus minutes. So from this data plot, we overlay the Thiess curve. And these two curves or these two graphs should have the same scale, meaning 1 to 10 interval should have the same size, and the data plot and the Thiess curve 10 to 100 should also have the same size, and so on. And then we basically manually move around the Thiess curve until we get a type curve that fits the data plot. And then we get a match point within the two graphs, and then we obtain the four important coordinates, which is the WU from the Thiess type curve, and then the 1 over U from the Thiess type curve, and then the drawdown from the field graph or the data plot, and then time from the field graph or the data plot. So sorry, this is actually small t. Time is just small t. Alright, to make it more clear, this is an example. So this is the data from well testing. So we were pumping out groundwater from a well, and we are recording the drawdown or the change in water table level. So that's your drawdown. And then we're plotting it versus time in a log scale. So this is log, this is in log scale. So drawdown is in your y-axis and time is t. Alright, so so of course your drawdown will be increasing over time because you're pulling out water from your aquifer, and you get this plot. Alright, so this is your data. That's your data from the well testing. And then what we do is we overlay this dude here. This is the Thiess type curve. So the Thiess type curve is a set of mathematical curves. These are mathematically derived curves that approximate different well conditions. So they are sort of ideal curves which represent different well conditions. So we take this ideal curves, and then we try to overlay it on the data plot. Okay, so note that they have the same scale here. So 1 to 10 in the Thiess type curve has the same size as in the data plot. Okay, so 1 to 10, 1 to 10. So they have the same sizes. All right, same sizes, same scale. So we just move around these type curve, all right, until we find a type curve that actually matches our data plot. Okay, so once we find the match, like like here, we have a match here. What we do is we pick any, or we just pick an arbitrary point. So we just pick any point within the graph. Pick any point. It could be here, or it could be here, or it could be here, it could be anywhere. But for convenience, for the ease of calculation, it's just best to pick a point that coincides within a whole number here. So for this example, we picked a number that is equal to WU, where WU is equal to 1 and 1 over U is equal to 100. Alright? From there, we also have to read out the equivalent drawdown at that point, and the time t at that point. Okay, so to be more specific, this is what it looks like. So this point has four coordinates: the w, the 1 over u, the s, and the t, and these are their values. So w is 1, 1 over u is 100, and then s here is somewhere between 1 and 0 and 1, and is actually equal to 0.41, and then t is somewhere between 10 and 100 minutes, and this is actually equal to 21 minutes. Okay, so you have these four coordinates, all right, from this match point. And then what we do here is we just start plugging in the values of u and t. Sorry. We start with we start first with this equation. So we know the W, we know that, check. We also know the discharge, which is the pumping well, which is the rate in which the well is pumping. So we know that. We also know S, or the drawdown, check. Then you also know 4 pi, which is 4 times 3.14. So we all know these inputs. Just plug in all those numbers and you will get transmissivity. Alright, so you get transmissivity, and then the next step is to get the storage coefficient. Big S. So all you have to do is just plug in your transmissivity from the previous solution. Plug in time from the coordinate of the time coordinate, which is 21 minutes. You also plot u from 1 over u. So you just invert 1 over u to get u, and then multiply it by r squared. All right. So basically, that's how the Thiess equation works. All right. And the Thiess equation has a lot of modifications, like for unconfined aquifers, confined aquifers, and so on. And there's actually a computer program to do analysis using the Thiess equation. And that program is the AQT-solve by Hydrosolve. Although, as with all calculations, you have to have a basic competency of the manual calculation, so that you can always do a what we call the sanity check of your computer calculations. So sanity check is just to make sure that the numbers that you're getting from your program or your model or your Excel is actually reasonable. Okay? So sanity check is what we do to make sure that we're not missing out anything, or the program that we are using has no bug or so on. Okay? So we always double check everything, or triple check, especially in hydrogeology, because simple mistakes can easily result in big, really huge errors. Okay? That concludes this lecture. All right. Thanks for listening.